Thanks so much, Craig, for organizing, and thanks to everyone who's making time to view this presentation. I'd like to take the opportunity to talk to you about stochastic approach for ice sheet surface mass balance and how that plays into sea level projections that we're able to generate for coastal planning. So first, I'll talk about why we might want to use a stochastic approach. Later, I'll talk about how we can choose a temporal model that will account for variability in observed Greenland surface mass balance or modeled Greenland surface mass balance based on process models. Then I'll talk about accounting for spatial variability across the ice sheet. And finally, I'll outline the path forward based on this work and leave time for discussion and questions. So the motivation for me, a major motivation, is this slide, which may be familiar to many people in this audience. This is an image from Golzer et al. 2020 showing a wide range in projected sea level rise. So this is the range of Greenland's possible sea level contribution under several different general circulation models, which are the colors, with multiple ice sheet models participating, the shaded regions, and two different climate scenarios for comparison. So what we can see from this image is that out to 2100, the climate scenario that we follow as a global society matters a lot, but also the representation of ice sheet physics matters just as much. So the specifics of the model that we're using account for a wide range in how much sea level rise we might expect. So that affects our ability to plan for it. The literature from coastal planning tells us that planners would like probabilistic projections. So I've included two examples here. One on the left from the Journal of Coastal Research, saying that planners would ideally like a projection of a particular sea level rise to be associated with a certain probability. And it's not useful for planners if that entire range, that wide shaded region that we saw on the previous slide, is assumed to be equally probable. So it would be useful if we were able to quantify within there which are the most likely portions of that range. And on the right, I've included a quote from the US National Park Service talking about a lighthouse modification, saying the Cockspur Lighthouse revetment will be modified to protect against sea level rise over the next 20 years, assuming that the current rate of rise will continue, and indicating that their project design would be improved if they were able to quantitatively evaluate risk and use a probabilistic projection for what risk they estimate to the lighthouse that they're trying to protect. However, unfortunately, with these demands for probabilistic projections, ice sheets make it difficult to generate probabilistic projection. It's questioned whether precise probabilities can be quantified, among other reasons, because of deep uncertainty in ice sheet responses. When we say deep uncertainty, we mean that the probability distribution of the inputs is unknown, for example, which consequences should be considered and the ranking of their importance. So in particular, the probability distribution of inputs to ice sheet models. So for example, how surface mass balance of the Greenland ice sheet might change in various climate scenarios is not well understood or constrained. We have some process models available to us to do that, but it takes a while to sample the whole range of possibilities. The methods that we have to generate projections of sea level rise tend to limit our ability to generate these kinds of probabilistic projections. So here I'm going to fill in a spectrum from simple to more complicated methods. This image shows a semi-empirical method where a projection of sea level rise is associated with a certain system variable, in this case, temperature. And in this case, many simulations are possible. We can sample a wide range of climate futures, but the sea level rise at a given temperature, that function is assumed to be similar to the past. And so if there were to be large changes in the relationship between temperature and sea level contribution, for example, through unpredicted or poorly constrained ice sheet dynamics, this type of method would not be able to account for those changes. On the more complex end of the spectrum, we have ice sheet process models and models for the various processes involved in ice sheet dynamics. Process models can evolve dynamics, and so a future fundamentally different from the past is possible with consistent physics, but the computational expense of these models means that we can't do as many simulations as we would like to fully characterize the wide range of future possibilities, rather. So somewhere here in the middle, we can put a stochastic model, which allows us to sample the variability from the process models that we have. So taking some of that output, but simulating many future scenarios through statistical methods to fill in the range of possible climate futures. Another challenge facing us in generating probabilistic sea level projections is that ice sheets themselves tend to amplify internal climate variability. And so here is a video from a recent paper by Roble, Sarusi, and Rowe, showing the anticipated sea level rise contribution from Thwaites Glacier given decadal variability in ocean forcing. And what you see moving across the bottom is a probability distribution of global mean sea level rise contribution from this glacier, changing over time. And what you see at the top left is the maximum ocean melt rate, which is variable. And at the top right, you see the retreating grounding line of the glacier. And what you can see from this simulation is that the probability distribution of sea level contribution spreads out, and many different possibilities become approximately equally probable. So it helps to treat it as stochastic. So that is the motivation for the Stochastic Ice Sheet project, which is managed by Alex Roble at Georgia Tech, and where I did some postdoctoral work a couple months ago with a larger team at many institutions, including Dartmouth and Caltech, building on the ice sheet and sea level system model. So here I'll talk about surface mass balance, and the Stochastic Ice Sheet project aims to target several different components of ice sheet variability and allow them to be generated stochastically. I think, yes, okay, very good. The ultimate goal of the Stochastic Ice Sheet project is to be able to facilitate ensemble simulations for projections, so allowing us to generate those probabilistic projections that I mentioned are useful for coastal planning, and also enable attribution studies, so studying both the past and the future evolution of the Greenland ice sheet. This makes it easy for the user of the ice sheet model to test a wide range of uncertain parameters. They can run an ensemble with several different samples from a stochastically generated process. And this is not intended to replace process models. So I'm not here to tell you that stochastic surface mass balance is better than process model generated surface mass balance. Rather, we should envision this as a complement to process model contributions that will allow us to extend the utility of the process model simulations that we already have, including attribution of past observed changes through large ensembles of the past, hindcasts, and also help us focus on priority areas for refinement. So we'll be able to partition uncertainty and find what parts of uncertain future sea level contribution are attributable to what uncertain components in the ice sheet input and processes. So a spoiler of what I intend to present to you, you'll see this later on. We here will construct a stochastic model to generate possible surface mass balance futures at minimal computational expense. So here's an example of catchment surface mass balance in Kangerlussuaq catchment, Greenland, where we have a single process model in black and 100 or maybe even 1,000 here stochastic realizations in blue, going out to 2050. And this generation from the endpoint of the process model in 2012 to 2050, all of these together take a few seconds on a laptop to generate. So this is the kind of computational input that we are after. So here, a first test of this stochastic method that we intend to apply across different processes on the ice sheet. I'll generate stochastic surface mass balance. So the goal here is to produce surface mass balance fields that reproduce key features of process model output. So I've highlighted here again where the stochastic model sits in between semi-empirical methods and process methods on the scale of complexity. And we want to take the insight and information that we get from process modeling and reproduce that with less computational expense in a stochastic model. So the plan of what we're going to tackle here is to identify a statistical model that can reproduce the variability found in simulated surface mass balance. We're going to identify a best fit or preferred model using the Bayesian information criterion. This is commonly applied for model fitting, and it tests both goodness of fit and penalizes overfitting. So making sure that you don't have more parameters than you need to fit the data that you have. We're first going to fit temporal variability, and then we'll account for spatial variability, which I will discuss later on. Okay, so this equation here at the bottom, I'm now going to gloss. The fitting of the statistical model that we're trying to do is to express the surface mass balance at a time as a sum of a constant term, this beta naught, a linear trend over time, beta 1t, a possible seasonal cycle, variation summer to winter, for example, a dependence on past values. So this is an autoregression in this format that I've shown it here, and then a residual epsilon t. So I'll talk more about the residual later, but for now, we'll focus the model selection on these two components, the dependence on past values and the residual. We're able to find the constant linear trend and seasonal cycle from the data, take those out and add them back in later. The first question that we need to address is which process model output we should attempt to reproduce. And there are a couple of sub-questions that we want to think about when we're identifying what process model output is useful for us. So first, how long should the training data set or the process model output that we're trying to reproduce be? We need to think here about the role of natural variability. So for example, the Atlantic meridional overturning circulation, which has an anti-correlation with Greenland surface mass balance. So when the overturning circulation is strong, bringing warm water to southern Greenland, you can see changes on the time scale of 40 to 60 years, depending on location, in Greenland surface mass balance. So do we need to account for that? We also need to think about our intended use case. So here I'll highlight multi-decadal sea level projection motivated by the coastal planning that I indicated at the beginning. That's what we intend to do for now. We can build on this method and reevaluate later on if our goals change. And next, we need to think about what data is available to support our goals. So we would like the process model data that we're reproducing to be spatially distributed. This is a reason to look at process models that simulate the whole ice sheet instead of a single catchment or instead of a single ice core reconstruction, because we eventually want to force an ice sheet model with the surface mass balance. We also want it to be model agnostic. So we don't want our stochastic method to simply reproduce the preferences or the vagaries of a single process model. We want it to be representative of the best or consensus idea of how Greenland surface mass balance varies in time. So here is just an excerpt from the Greenland surface mass balance MIP paper comparing the surface mass balance mean, standard deviation, and trend across 13 different surface mass balance models. This is the motivation for wanting our stochastic method to be model agnostic, because there's a lot of difference in both the mean and the standard deviation of 20th century surface mass balance among process models. So we want to make sure that we can capture all of the different behaviors of those process models in something that we're going to use to simulate the future. To answer these questions, we can turn to ice core reconstructions. So we ask how long data sets should be to capture the major variability first. And here I've plotted the autocorrelation function, or the partial autocorrelation function, from an ice core reconstruction of surface mass balance in the grip core over 100 years. So the partial autocorrelation function can tell you what order of autoregressive model might be a good fit for your data. So I showed you that temporal model that we're trying to fit, and this helps us identify what candidate models we want to use here. The shaded confidence interval here is around 0, and points outside of it have a partial autocorrelation significantly different from 0. So I'll highlight here, and I want to draw your attention to the very strong autocorrelation at 1 year lag, and to a certain extent, other short timescales. Across cores, we see that short lags of 0 to 5 years are the most important to include in an autoregressive model of the type that we're going to generate. And I have looked at this core as well as several other ones that were available in the same publication. So across 5 cores, we see the most significant features at these short time horizons. So that indicates that we should include these short lags in our autocorrelation, our autoregressive model. We do see some longer term features, but they vary by core. These cores are taken at different locations. And so their response to things like the Atlantic meridional overturning circulation varies. And here we're going to focus on decadal scale process modeling in line with our goals to generate decadal sea level rise projections. I'll note here that these are autocorrelation functions calculated over 100 years. We also looked out to 500 years and saw essentially the same thing. The caveat here is that this is point data from ice core reconstructions. So the point data can really help us with these long records, but spatial resolution from, for example, a much longer run of a process model would really help us. So we have some longer simulations from 2 surface mass balance models, but if you have some more, we are happy to receive them. So here I'll focus on decadal scale and the data that is available from the Greenland Surface Mass Balance Model Intercomparison project. So here, Greenland SMB MIP was a project for 13 surface mass balance models to simulate Greenland surface mass balance from 1980 to 2012. They interpolated their results onto a common ice sheet mask with 1 kilometer resolution. And from these 13 models, we're able to take the output and analyze 7 of them: ANICE ITM, CESM, DEBM, HIRAM, NHM SMAP, RACMO, and SNOW models. So thanks very much to those developers who allowed us to use their data, and to Xavier Fetweiss, who provided it. So we're using the models that we have permission to use. Thankfully, it does sample most of the range of Greenland SMB-MIP participating models in terms of having different means, larger and smaller standard deviations. So this also, sampling multiple different models, can help us achieve our goal of stochastically generated surface mass balance that's model agnostic. So generating surface mass balance that agrees with what many process models do. We're going to reduce complexity by aggregating to catchment scale. In what I'll show next, we do not want to fit a stochastic model to each individual grid point. That would not help us at all in terms of replacing or enhancing process model output. So we're going to aggregate to the 200 catchment basins around Greenland that were defined in the Mugino and Rigno data set. And for each of these catchments, we're going to test a stochastic fit to 7 time series, which is 1 for each surface mass balance model. So here I'll be showing the catchment sums or the catchment means. So we have a single time series for each model for each basin. I'll show here some highlighted results for this catchment highlighted in blue, which corresponds to Congar-Luswak Glacier. Okay, so we have our process model data from Greenland SMB MIP. We've aggregated it to catchment scale, and for each catchment, we have 7 time series, 1 from each surface mass balance process model. Now we want to fit each of those series, each surface mass balance model and each catchment series with these components that I outlined in a previous slide. So we'll focus first on the temporal variability, this term in blue, the autoregressive component. We test several candidate temporal models. So here I've indicated what's known as an ARN, an autoregressive model of order n, where the value at present time depends on values from past times. We also tested some other candidate models such as ARIMA, which includes some differencing and a weighted moving average of several noise terms, as well as fractional differencing ARIMA, which has kind of a long memory. So if past surface mass balance values seem to be quite important for current ones, we might want to use one of those. But we use the Bayesian information criterion, as I described earlier, which measures goodness of fit with a penalty for number of parameters to choose among these candidate types of temporal models. And we find that ARN is strongly preferred in terms of Bayesian information criterion. So the difference in Bayesian information criterion between ARN and others is on the order of hundreds. So the strength of recommendation is very strong, as outlined in this table. To do the fitting that I show here, we're using some open source Python tools, which you can also use, the package stats models, and documented in a Jupyter notebook, which allows you to follow along and reproduce our approach. So first we extract and analyze monthly surface mass balance from all of the Greenland SMB MIP models that we have available to us. Here, these are 7 time series colored by the process model. year on the x-axis and the catchment surface mass balance. So here a catchment total in millimeters water equivalent on the y-axis. You can see there the monthly variability over about 30 years. And now I'm going to show an ARN fit to that. We have low order autoregressive fits are preferred in terms of Bayesian information criterion by a lot, but they still miss large peaks. So you see here the monthly series in blue of a single process model on the lower plot, and the AR4 monthly fit to it in black. It's missing a lot of peaks and troughs, and so we wonder if we can do better. We find that aggregating to annual scale, so looking at annual catchment surface mass balance, lets us capture the range better. So here I've aggregated to annual scale. So at the top is the same monthly time series you were looking at. In the middle, annual surface mass balance for each of these process models. And on the bottom, a similar low order autoregressive fit, this time to the annual surface mass balance. And you can see that the annual fit allows us to capture these peaks more closely. So you might wonder, as I did, whether annual aggregation is really okay to do. And there are a few reasons why we think that it should be okay. The first is that the ice sheet is a low pass filter. So even short time scale variability is going to be integrated by the ice dynamics, which is what we're trying to force, and end up with a lower timescale variability in the end in terms of the ice sheet response. Next, monthly misfits. So if we were to fit the monthly time series and then aggregate to the annual scale, or say sum the surface mass balance over a period we want to simulate, those could compound. And the same is not true if we look at annual scale and then try to go back to the monthly scale with residuals, for example. So here is a plot of the summed error in a single catchment for monthly in red and annual in black. And you can see that the summed monthly error generally matches or exceeds the summed error from the annual fit. So this is the compounding error that I mentioned. Finally, we're able to return to finer scale variability, so shorter timescales, in the spatial downscaling that I'll show momentarily. So we conclude that, yes, annual aggregation is okay as a first attempt, and we'll go back and clean up and get some monthly variability in there later on. With these annual fits, we find that for most catchments on the Greenland ice sheet, of the 200 outlet glacier catchments that we simulated, we found that the simplest available temporal model is generally the best fit. So we see that first order autoregressive models are quite dominant. They're the best fit for about 175 of the 200 catchments in this histogram. There are a few catchments where slightly higher order, more complicated autoregressive models would be better, but those preferences are not strong. So the difference in Bayesian information criterion between these higher order autoregressive fits and lower order autoregressive fits is much weaker than between simple autoregressive and more complicated types of temporal model. So in summary, what I've outlined thus far is how to fit a temporal model to the variability of the Greenland surface mass balance. I'm hearing some echoing. Matt Pierce, if you could mute your microphone, please. Thanks. Happy to answer questions, of course.
Yeah, sorry about that. I just caught the echo. We have a question that's just come up in the chat. Do you mind if I interrupt you?
Go ahead.
So there's a question from Kevin. I hope it doesn't mind. I'm just going to read it out so we don't spend too long. How relevant is a stationary autoregressive model to characterize future SMB, especially on the long term? Future SMB may be expected to be a non-stationary stochastic process due to increased variability over time.
Yeah, certainly. So the question asks whether we can assume that an autoregressive model that we fit on past data would stay the same in the future. This is certainly a major scientific question and something that we need to grapple with as we develop and apply a model like this. At short timescales, it's probably okay. At much longer timescales, so on the scale of millennia, we can see much more variability and imagine that things might be changing such that 30 years of data is not enough. This is a question that we are addressing with the longer simulations from process models that I mentioned. So we do have, for example, like a pre-industrial simulation from one of the process models, and we can compare a stochastic fit to that with a stochastic fit to 20th century SMB, for example, and see what are the differences in the fit that we find there. And that can help us, if not develop a non-stationary stochastic process, at least interpret the results of the stochastic generator that we have. So in V1, we're assuming stationarity and treating short time scales. As we develop and refine stochastic forcing of ISSM, we might be able to incorporate non-stationarity. Thanks for the question. I should also mention that this component, this autoregressive component, is only one of the sum. So I outlined, let's see here, on this slide, that we're breaking surface mass balance into several different components. We have a constant, linear trend, seasonal cycle, the autoregressive component in blue, and a residual, which will give us our spatial information. And we could imagine that this constant and the linear trend might also change over time. So that's something that we could handle outside of the stochastic fit. Okay.
Thank you very much.
So I've mentioned that we've fit a simple temporal model, which we can use on relatively short timescales, decadal timescales, to pursue some initial research questions. Our low order autoregressive fits are an acceptable fit to the aggregated catchment scale time series. Next, we'd like to account for spatial variability. So we found that AR1 is a suitable temporal model. And I mentioned just now in answering this question that there are several components of surface mass balance. The constant, linear trend, and seasonal cycle can be fit separately. Then we have this temporal model, the autoregressive model in blue. And finally, this residual term in purple, which is everything else that's not fit by the previous fitting. So this is what we've dealt with so far. This residual, epsilon t, can now help us account for spatial variability. So we can insert spatial information or find spatial information that's available and use the residual term epsilon to generate it. So following methods by Castruccio and Hu and Castruccio, we're able to use the residual term epsilon to generate a spatial interdependence among catchments here. So if we've done our job, this residual term epsilon t consists of independent and identically distributed IID, draws from a normal distribution with some variance sigma squared. The temporal fits and the variance could be different for each catchment. So I mentioned that we've done this for 200 catchments around the Greenland Ice Sheet. The spatial correlation matrix C captures these differences in catchment level fits. So the variance sigma squared includes a component of per catchment standard deviations, as well as intercatchment correlations. And if you're interested in these methods, I would encourage you to look for much more detail at these papers I've cited below. So now the per catchment standard deviations are what we can see from what we've already fit. Now we would like to look at the intercatchment correlations, which is going to give us the spatial information that relates catchments to one another. So we need to identify the correlation matrix C to construct spatially variable surface mass balance. This empirical correlation matrix is the correlation of the residuals of temporal fits between all of the catchments. So there is a lot going on here. It's the correlation of residuals of all catchments with the residual of the Conger-Lueswak autoregressive fit that I showed earlier. This is a 200 by 200 symmetric matrix. There are 20,000 relevant data points. And to make matters worse, our problem is undersampled. We have only 30 years of data for several hundred catchments. And so we need to control some instability in this matrix. We need to simplify this and extract only the most relevant information. So I'm going to plot this on a map of Greenland. This is the same correlation of residuals with the residual of the Conger-Lueswak fit. Dark red, it has a perfect correlation with itself. And you can see that there are spatial differences in which catchment surface mass balance seem to correlate with the residuals of this ARN fit. So we need to control some instability in this matrix. There's a lot more information than we can really interpret in this map. And we use the sparse correlation matrix, which is also possible with an open source Python package, scikit-learn, to control the singularity and find only the most relevant correlation information for a spatially varying field. So now we're going to use this sparse correlation matrix and put it back in here to generate this residual term epsilon t with a variance determined by the per catchment standard deviations and the sparse correlation C that we're able to generate from graphical lasso scikit-learn. This method generates appropriate residual time series. So in black, I have the residual of our autoregressive fit to a series from a single process model. And in blue, I have the residuals which I generated with the sparse covariance method that I just demonstrated, 100 realizations. And you can see that they sample approximately the range and the variability of this residual. So we've now fully specified a model for stochastic surface mass balance. We have the temporal components that I mentioned earlier, as well as spatial information, which lives in this residual term epsilon t. So we can put this together and look at stochastic realizations to a single process model. Again, for our Conger-Lewis example, and this is 100 realizations of surface mass balance over the simulated period, 1980 to 2010. It fills the range of variability. It has similar peakiness and spectrum, and this was generated without knowledge of the input data. So we just use the parameters, the constant, the trend, the autoregressive fit, and the spatial residual epsilon to generate draws or samples from the stochastic generator. And as I showed as a spoiler at the beginning, this model can easily generate possible surface mass balance futures. So this simulation out to 2050 with 100 realizations takes only a few seconds on a laptop and allows us to sample much more of the range of possible surface mass balance for short-term simulation and ensemble forecasting. So looking ahead, we would like to force an ice sheet model, ISSM. We've generated catchment aggregated time series that imitate the process model output. And next, we need to downscale this to something an ice sheet model can actually use. So generating surface mass balance for an ice sheet model is the last thing that we need to do before we can put this in ISSM. What we have is this catchment total surface mass balance series that I showed in the previous slides. What the ice sheet model would like, ISSM would like grid scale surface mass balance. And so instead of one time series per catchment, we need to think about the surface mass balance changing at thousands of grid points within each catchment on a 1 kilometer grid scale. What we can do here is fit an elevation dependent scaling factor to convert the catchment mean to a value at each grid point. And so here I've plotted the surface mass balance anomaly per month for a subset of points within the Conger-Lewis catchment. And you can see that the anomaly, or the difference between the catchment mean and each of these points, is spatially variable and also variable in time. So each of these points can have a different relationship to the catchment mean time series that we generated with the stochastic method. So this elevation dependent scaling factor, secret, it's really just a mass balance gradient. We're going to fit a function with elevation and surface mass balance anomaly to convert the catchment mean to a value at each grid point per elevation. This month-by-month climatology also helps us convert the annual stochastic series to monthly input. So I mentioned this varies in space as well as in time. And here I'll just highlight that the winter scaling, for example, month 1, January, is different from the scaling that we would use in the summer, month 6. So this allows us to take our annual catchment aggregated time series from the stochastic generator and produce a local grid scale monthly series that the ice sheet model can actually use. And with this in hand, we can generate a series for each grid point of each catchment. And we only need to save a few parameters to be able to do this. The stochastic generation is very fast, and we scale it the same for the entirety of the simulation. Looking ahead, we're looking to build stochastic forcing into ISSM. So I've talked about generating stochastic surface mass balance in this talk. And the ongoing work is to modify ISSM to enable a stochastic option. So the user would be able to say, I want to use stochastic surface mass balance forcing, or I want to use stochastic ocean forcing. And Vincent Verjans and Helen Sarusi are working on that right now. Other components of the project will look at stochastic ocean thermal forcing, as well as eventually iceberg calving and perhaps basal dynamics. I don't know, Alex, you can think about that. And the ultimate goal with this stochastic ice sheet system model is to support sea level projections with robust uncertainty quantification. So an example application is to be able to sample many more ensemble members and determine probability distributions within these ranges, given a wide range of uncertain parameters, so that we can report to coastal planners what is the most probable section of the estimated range, and what are the causes or sources of remaining uncertainty. Everything that I've demonstrated today is archived on GitHub. So there's code and a Jupyter Notebook guide in this GitHub repository, which you are very welcome to access and comment on, or work through and let me know your questions. So to summarize what I've mentioned today, we found that very simple low order autoregressive models are sufficient to capture the interannual variability of Greenland surface mass balance in the late 20th century at catchment scale. We're able to use this information to construct fields that vary in time and space using, sparse spatial covariance, and ensemble simulations that are streamlined by a stochastic method like this can support projections of a 21st century sea level rise with robust uncertainty quantification, and hopefully support coastal planning and other societally relevant applications of sea level information. Everything that I've produced here today is open source. Here are some packages that I've used, and the work was funded by Heising-Simons Foundation and led at Georgia Tech. So thanks very much for your time, and I'm glad that we've had some time to discuss here as well.
Thanks ever so much, Liz. That was fantastic. Do we have any questions from the group? Ruthy's clapping. Alex is also clapping. Let's give a moment, perhaps someone is struggling to unmute. We have a question from Jeff Ridley, it appears. Jeff, would you like to unmute?
Hi, Lizzie. How do you think this changes is different than the work in ISMIP 6 and I know Tamsin Edwards' stochastic approach?
Yeah, so Tamsin is working on emulation approaches. I'm actually not very familiar with the statistical details of her approach, so I can't comment in detail about what is distinct in our approach as compared with hers. I do know that we are looking in detail at process models and our model agnostic, so we're able to look at variability as is captured in multiple process models. I think that Tamsin's approach, if I'm not mistaken, also aims to emulate a sea level projection directly. And so there is a statistical representation of some parameters, some input parameters that ends up in sea level projection. This is aimed to stochastically force an ice sheet model so that certain components of what goes into the physics can be stochastic and certain ones can be deterministic, which means that you end up with sort of a mix of stochastic and deterministic contributions in your simulation, depending on your choice.
So the biggest effect on ice sheet from uncertainty point of view is the sliding, basal sliding, and so Tamsin did a lot for CMIP 5 as well as CMIP 6 regarding running models with different sliding parameters, and then seeing whether they could be emulated in a similar way. But of course, there's a lot of Antarctic basal sliding where if you lose an ice shelf, then it changes, and so you can't just stochastically do that. There's tipping points effectively. I mean, you can't deal with that, can you?
Right, absolutely, and that's why I mentioned that in the outline of wish list and things that we would like to do, basal dynamics maybe eventually. So surface mass balance, what I've presented here, is an accessible first step of a stochastic forcing that we could put into ISSM. We have a lot of data available about surface mass balance, spatially resolved fields, which are observable at the surface. Basal dynamics and the sliding law, as you mentioned, have to be inverted generally from surface observations. And if you change conditions, then the inversion might change a lot. So the observational or process-based constraints on basal dynamics are not as robust as we have for surface mass balance. So that is for sure one contribution that Tamsin's work has made, sampling a range of basal sliding that we have not tackled yet and probably won't in at least the next couple of years. Alex, maybe you have thoughts about that. Or not.
I could add to what Liz said. I think she answered the question pretty well. I think the key point here is that we can simulate those things in ISSM, right? Like the nonlinear changes in ice sheet dynamics, the tipping points as people call them, that happen in ice sheet dynamics. What is challenging to simulate are the many different realizations of climate forcing that might occur in the future. And so approaches like this are parallel to approaches like Tamsin's approach using a Gaussian process emulator to sort of sample the space of parameter uncertainty. We're not necessarily trying to tackle the parameter uncertainty problem, which other people are doing, using other approaches. The point here is really to focus on the fact that there is intrinsic uncertainty in both forcing and certain ice sheet processes, which, using a stochastic parameterization, we can, potentially try to estimate what the resulting uncertainty in sea level projections is from that intrinsic uncertainty.
Yeah, so if I could summarize, I think that Alex has indicated, and Jeff has also described Tamsin's work on parameter uncertainty within the ice sheet dynamics, so things that we don't have a good handle on about how the ice sheet itself behaves. Those are things that can be simulated by a process model like ISSM, but things like surface mass balance and ocean thermal forcing are interconnections between the ice sheet and the climate, which itself, the climate has internal variability that needs to be accounted for, and it's very difficult to sample those using traditional methods. And so that's the contribution of using a stochastic forcing in addition to stochastic emulation of parameter uncertainty.
We have Jeff has his hand up. I think there was a question or a comment from Kevin in the chat. Kevin, would you like to unmute? And I know it's just a comment, but it's nice to hear from the range.
Yeah, actually, I just wanted to say that stochastic modeling and emulator are basically two different things. If you think about an emulator, I would say that some kind of computationally tractable approximation of a a very computationally expensive ice sheet model. But we still need to characterize the uncertainty in the input variables. And this is why stochastic modeling is so important. So these are basically two different things. An emulator is more to propagate uncertainty into a computational model. But first of all, we need to characterize the uncertainty. So these two things are, in my point of view, totally different.
Thanks, Kevin. That's helpful.
And also, I like to mention that usually emulators are used for a few sets of parameters. So these are typically scalar parameters. In your case, what you're doing is basically trying to model something that's spatially and temporally variant. So this is in theory an infinite number of stochastic variables. So I'm not even sure that using an emulator would be relevant in the case of a stochastic temporal or spatial forcing. So, okay, this is just my point of view, but usually, yeah, emulator cannot really deal with a large number of input variables.
Yeah, absolutely. Thanks, Kevin. So yes, what we're generating here are time series and time varying fields eventually, with a value at each grid point that can change in time with the stochastic generator. Whereas an emulator might allow you to sample very densely within a range of scalar parameters that could be assumed not to vary in time or to vary only simply in time.
Thanks ever so much, Kevin. We have Jeff. Jeff's got his hand up. Jeff, do you have another question?
Yes, there may be an alternative use for this stochastic forcing concept, in that when you spin up a coupled model ice sheet, you want to spin it up offline for, say, 1,000 years or more, and so the variability of the atmosphere, people often use the climatology to run it, spin it up, but actually the internal variability isn't expressed in the climatology. So a stochastic method might be a good way to do that.
Yeah, that's actually a great point. I had not thought about that. I'm sorry, go ahead, Jeff. I didn't mean to interrupt.
Yeah.
Yeah, that's a neat idea.
Yeah, using stochastically generated surface mass balance to spin up an ice sheet model is something that we haven't thought about yet. We've thought about past simulations to attribute change to either natural variability or anthropogenic changes, for example, or specific modes of variability, but we haven't thought about using this to start up the ice sheet model, apart from inputting it as a forcing to ISSM. So you could, if you wanted to, spin up an ice sheet model using a climatology or a stochastically generated estimate of the climatology, and then run it with your favorite surface mass balance, perhaps the process model that the stochastic generator was representing for the 1,000 years.
Thanks, Jeff. Do we have any other questions or points from the group? Silence, very quiet. Thanks again, Liz, ever so much for talking this morning. I'm really looking forward to putting this up and adding it to the series. Yeah, thanks again, and it's great to have you. If there's anyone that you would like to see in this series, please let us know, and I'll try my best to get them in. I'm going to log off now for everyone. For those of us at GIST, there's another meeting coming up, which I'm sure you're aware of. Just another quick friendly reminder of that. Okie doke, so thanks everyone for joining us, and we'll see you all next week. Thanks again, Liz. Hope you all have a great day.
Thanks, everyone.